Good morning, everybody. Thanks for attending this, and hope it's worth your while. This is something I had presented in the past, and I've sort of revised in Bayesian, classic Bayesian thinking, I've sort of revised my thoughts and expectations on this, and I'll explain that as we go forward. But my name is TJ Turnage. I'm a meteorologist here at the Weather Service in Grand Rapids, and the idea here is to try to describe the concept of Bayesian thinking and how its use of probabilistic thinking is maybe going to apply to weather forecasting as well as all other aspects of life where uncertainty is involved. So my motivation for doing this is based on, of course, there's an increased emphasis in probabilistic thinking in the weather enterprise and really a lot of other facets of the world. And so probabilistic forecasts do require us to think probabilistically, of course, and that's a concept known as thinking in bets. That's a critical skill, and I'll talk a little bit more about that. Training on probabilistic thinking has been somewhat lacking, although we do see that changing. There are some courses that have been released on ensemble fluency and the like. However, thinking probabilistically specifically is maybe a little bit new, particularly in a Bayesian framework. So this hopefully provides just an introduction to it. My main sources for this talk are really these three books here that I have listed. I'll try to give attribution when appropriate. I borrowed a lot of their examples directly, and I highly encourage you reading all of these if you get a chance. They're really very kind of life-changing books in a way, you know, the way I think about a lot of things in this profession, and maybe you'd find that to be the case too. So one thing I should say, backing up a little bit, is I had created a YouTube presentation on this topic a while back. I think it was like in August of last year. And if you may have watched it, and if you did, you'll notice that this presentation is going to be quite different because, first of all, I use different examples. But even more important than that, I've come to really believe that I made some potentially serious incorrect assumptions on that video. And I'm going to try to explain that and remedy that here. So the fact that I'm kind of shifting course a little bit, that ought to tell you that I'm far from an expert on the topic of Bayesian thinking. So what is Bayesian thinking? Well, it mainly consists of three steps. It's a systematic way to, first of all, you're assigning an initial prior probability related to some diagnosis or to forecasting. It's like a first guess. Then you've also got to take into account what might affect the forecast outcome. Why might it be right, or why might it be wrong? And that can be pretty involved, as you might think. And then the next and final step is to update probabilities using that new information. So basically, you're going to have an updated probability based on maybe an outcome, and you're going to cycle that back into the Bayesian thinking process. And we'll go through some examples of that. So very first step is assigning an initial prior probability. And if you're gonna take one thing away from this presentation, just one thing, I hope it's going to be this slide, because this really is sort of a linchpin for Bayesian thinking. You know, whether you realize it or not, you're frequently assigning chances in the decisions that come up in your daily existence. Even though you don't maybe always put an exact percentage on it, we're constantly making first guesses that something will or won't occur. And so I encourage you to really think of everything as a bet, to actually put a number on it if you can, because if you do that, it's going to make you be a lot more process-based instead of outcome-based when you're in some kind of decision-making endeavor. And this allows you to avoid something that's called resulting, that Annie Duke had talked about in her book, Thinking in Bets. So there's a great example of that. In fact, it really stuck with me when I read her book, to the point that I want to share it here. So if you don't know, Annie Duke was a World Series of champion poker player. You know, she has a psychology background, but she's obviously very good at understanding decision making with limited information, given her poker background and also her academic background. Well, there was a time she was talking about where she was at a charity poker tournament. You know, it was not really a high stakes thing. It was just kind of a fun event. And she was there as a color commentator, just kind of watching some hands that were being played. And she noticed in one case that a particular player's hand had a 76% chance of winning, you know, just going off the kind of after the analytics and the statistics. Well, it turned out in that particular case, the outcome was the hand lost the round, that particular round. In fact, somebody even in the audience said, Annie, you were wrong. Well, so the question is, was she wrong? I would say no, she wasn't. She gave the best answer, even though it wasn't the quote right outcome. And that's the trap you can get into with resulting, where you can just really latch onto a particular outcome and you think of that instead of the process that went into it. So the answer that she provided was still the best answer. Now, notice I didn't say the right answer. I said the best answer, because you're never going to really have the exact right answer in a situation with limited information, which pretty much describes every situation. Okay, so let's give some examples of assigning an initial or prior probability. And it doesn't have to be sophisticated. It can be just a very simple guess. Even if you don't know, just throw something at the wall, you know, just put something out there. The only thing I would say, though, is if you make it 0 or 100%, that's basically going to short circuit the process. You're really never going to budge out of 0% or 100% if you start that. So it's a very, as we'll see mathematically, that's kind of a, you know, that's kind of a proof that being stubborn is, you just can't budge out of being stubborn, right? So the key is start with a simple guess. It may be informed, it may not be, but it's a guess, and it's between 0 and 100%. So here's some examples. So for example, let's say that you're in an area where, you know, climatologically, thunderstorms are very rare this time of year. And so I'm going to start with a 2% chance, even before I look at the guidance. So I'm assigning a probability. Now notice that you can have different levels of intelligence with that. You could be just completely guessing with the number, or you may have some kind of expertise built up where you have kind of this background climatology understanding of what's normal, what isn't normal. Of course, that's really helpful. But the good news is with Bayesian thinking, you should still theoretically converge towards the best, you know, answer, the best solution, even though maybe it'll take you a little bit longer if, say, you don't have a really good grasp of what a good first guess would be. Here's another example. This is kind of more of a, almost like a psychology type of thing, but let's say that you have a friend who has a friend, they want a loan, and you're deciding whether or not to do it. So you trust your friend almost implicitly, you know, 95%, and you trust other people 50%. These are just sample numbers I'm throwing out, right? So I'm just trying to emphasize the idea that everything is like a proposition. You can make it that way if you want. You can make it an actual bet and put a number on it. And here's yet another example, kind of tipping the hat to poker. So I got an example here of a young and kind of swagger type of poker player, and we'll just say initially there's a 45% chance that he's going to bluff on any hand, which is definitely more than average. Now, the second step, and this is where I really have kind of had to circle back and figure out how this works, and I will explain that a little more, but you really have to account for how the forecast is going to go right or wrong. It's hypothesis testing. So there's kind of two ways to look at it. One is, how likely is the event to happen when it's forecast to happen? So notice there's two things involved there. One is you're given a forecast or a probability of something. The other component is, well, how likely is that to occur, all else being equal? So here's an example where maybe we've got ensemble guidance. It's giving us a 54% chance of exceeding 8 inches of snow. Well, you know, even here in Michigan, getting an event that exceeds 8 inches is not what you would call common. I mean, it's not rare either, but it's a little on the more uncommon side. Whereas if you take the opposite, how likely is the event not to happen when it is forecast to happen? Well, in this case, if you play the percentages, that would, I guess, mean 46%, right, instead of 54%. But the other thing to take into account is it's actually more common to experience something that's under 8 inches than it is something that's over 8 inches. And so that actually plays a role into the hypothesis testing. Then the final step is you'll revise your expectations based on the new data or past outcomes. So going back to these examples that I was talking about earlier, let's say the model guidance is continuing to really be pretty aggressive for thunderstorm chances, even in a climatologically rare setup. So maybe you'll raise the POPs now to 30% probability for thunderstorms. Maybe the friend's friend defaulted on their loan, and so now you're maybe not trusting your friend as much, or you're just got a lower opinion of humanity in general, or both. And then with the poker player example, maybe they aren't folding as much, or they are folding more than you think they are. They seem to be playing a little more conservative than you would have guessed. So now you're going to say, well, now maybe only a 30% chance of them bluffing on any given hand. So this adjustment process is ongoing all the time, right? You kind of circle that back into a new prior probability as new information becomes available. So you're kind of calibrating your expectations. So this should sound very familiar, right? I mean, this is what we do all the time in life. Based on outcomes, we kind of reevaluate things, probabilities, that type of thing. Okay, so to give an example of how we think probabilistically, this is an example that came right out of a book called Thinking Fast and Slow. And so here's the hypothetical example. You got two cab companies. One is green and one is blue. A cab is involved in a hit and run in the middle of the night. So you got an eyewitness who said it was a blue cab, and this eyewitness is tested, and they're 80% accurate in these situations. Don't ask me how they're tested. The idea here is you can basically think of the eyewitness as like a forecast model that's right 80% of the time, right? So what does that mean then? Based on the information you have there, what's the probability it's a blue cab? You probably would say 80%, because you're going under the assumption that, yeah, there's probably an equal number of green and blue cabs. And if this person's right 80% of the time, we're going to say there's an 80% chance it's a blue cab. Very reasonable assumption. But what if I now tell you that 85% of cabs in the city are green and the rest are blue? So think about that for a minute. You're forecasting, or you're saying something is happening that, with the background climatology, so to speak, blue cabs are not super common compared to green cabs. In fact, they're quite uncommon. So you're forecasting something that's uncommon with 80% accuracy. So how does that flesh out? Well, it turns out the answer is going to be around 41%. And so let's look at why that would be. To kind of think about this, you have to treat, and I've sort of mentioned this before, and I'll repeat it here, is when you're trying to evaluate probabilities, there's actually two independent components, right? One is there's the forecast of the cab being identified as blue, and then there's the actual reality of whether the cab is blue or not. So those are two independent things, and there's a kind of connected probability of a correct prediction being 80%. So realize, first of all, that this is just a yes-no. This is a binary yes-no forecast. We're not even really talking about like ensembles or probabilistic or anything like that, okay? So this, in that sense, is fairly simplified, but even so, it's got a lot of nuances here, because if you think about it, there's four possible possibilities, four possible outcomes. One could be that the forecast is true and positive. In other words, the cab was forecast as blue and it is blue. Another possibility is a false positive, which is the cab is identified as blue even though it isn't blue, it's green. And then there's also true negative, which I'm not going to show here, but that means you correctly forecasted it not to be that, right? And then there's a false negative, which is kind of weird to think about. But fortunately here we've got only two things we really have to think about, which somewhat simplifies things. So the way you plug it in here is, so let's start with a true positive. You'll notice that not only do you have to figure out the cab identifying as blue, being given that the cab is blue, which is essentially like the reliability of the forecaster, but you also have to know what the background probability of the cab being blue in the first place is, right? And so in this particular case, you're getting 0.8 times 0.15, so your chances of having a true positive is 0.12. Whereas with a false positive, the probability of a cab being identified as blue given it's not blue, well, that's where the 20%, maybe that's where the wrong forecast comes in. So a 20% forecast times the background probability of the cab not being blue, which remember is going to be pretty large here since there's a preponderance of green cabs in the area. So when you multiply those together, you get 0.17. So it's interesting because your chances of having a true positive are less at 0.12 than they are having a false positive at 0.17. So what is Bayes' theorem exactly? This is kind of the linchpin here. The idea is that if you to get a posterior probability, to get an updated probability, you're taking the true positive divided by the sum of the true positive and the false positive. If we plug it into this particular case, that's how we get our 41%. And so one thing to note here is that if you have a large potential for false positives, that's going to reduce your posterior probability just right out of the gate. And so we can look at some examples of that. Let's circle back to this now before we do that, however. So what happens if you get more confirming evidence? So this is the same scenario that we left off with, right, where I just had told you that 85% of the cabs in the city are green. But now let's add another facet here. So let's say now there's another independent eyewitness that's not at all influenced by the first eyewitness. They also have an 80% accuracy, and they also say it's a blue cab. So now what's the probability it's a blue cab? This is how we update our prior probabilities. So now we are, instead of the prior probability of 0.15, we already have a greater expectation, a greater probability that it is a blue cab. So we're starting with 0.401. And if we run through the numbers, notice that the chances of having a true positive are now 0.33. Chances of having a false positive is 0.12. So you actually got nearly a 3 times greater chance of having a true positive than a false positive. And so what that ends up being is now you're at a 73% chance that it's a blue cab. And that's different, right? Because if you told people that 2 forecasts of 80% and you didn't tell them anything else, they would say that's an overwhelmingly good chance of it being a blue cab. But in this particular case, it's still 73%, which is high, but it's not really as high as you would expect it to be. It's certainly less than 80%, right? So very, very non-intuitive. All right, it becomes evident that the prior probabilities, the sensitive to the background probabilities, this is where it can be really evident. So if you're forecasting something rare, that is where there can be a lot of sensitivity. And so let's say that we're trying to diagnose a rare cancer that for this particular type in this particular age range, there's about a 1.4% chance of any person having it. The probability of having a true positive with a given test is 0.75. So if you take the test and you get if you get a positive with it, seems like a pretty good percentage, I guess. But then there's also a probability of a false positive that we're giving with the same test that is 1 in 10. That's 10%. So of course the question is, if you get a test yielding a positive result, what's the probability of actually having that type of cancer? Well, the answer is non-intuitive because you're starting with such a low initial possibility of having cancer, right? It's only 1.4%. That really lowers the amount of the true positive. So notice that if you multiply test as cancer given the patient has cancer, well, okay, we said that's 75%, but then you've got to multiply it by this background probability that's extremely low, and that ends up giving you a true positive of only 1%, 0.01. We were given a false positive of 0.10, and when you plug in the numbers, you get a posterior probability of 10% or 0.1. So that's interesting that you get a positive on a test, and yet your chances of having cancer are still very, very low, just because the population has such a low incidence of cancer to begin with. Now, if we run it through, same as before, we'll do the updated information. Our new prior probability is going to be 0.10 instead of the 0.014. I won't do all the math for you, but the answer ends up being about 43%. So you got two positive tests, and you still are less than 50%, which is very non-intuitive. Okay, so enough with all the other stuff. I'm sure you're probably more interested in the weather forecasting. That's kind of what was advertised here, and so now we can finally get on with it here. So here's a scenario, and this is sort of what I had talked about in the YouTube video that I did before, and I'll explain how it kind of deviates from my previous thinking. So the scenario is this. You've inherited a 40% probability of precipitation pop. You've got new model guidance coming in that gives you a 60% pop. And so how do you adjust the forecast? In the Weather Service, we're basically taking the latest forecast, right? The latest is the greatest, so we're going to 60%. If you run the numbers with Bayesian Bayes theorem, you're actually going to get something closer to 55%. Now, what I did before in the YouTube video I did is I said, okay, I'm going to run with this idea of starting with a 40% pop. And let's suppose that you're getting model run after model run that's just giving you a pop that's always the same. What's the outcome going to be? Well, if you run the numbers, this is what you get. So let me explain what this chart is. So looking at towards the upper left, 60%, that's saying that we're running through repeated forecast cycles. Every single time the new model is saying 60%, 60%, 60%, okay? The column that says first iteration, the very first time that you run the model, you're going from that 40%, remember that's what we began with, you're going from 40% to 55%. If you keep running the model again and again, you'll eventually converge on a pop of 67%. That's the third column. So if we look at other forecasts of 70, 80, and 90%, you'll see what happens with that. Generally speaking, you'll end up higher than what we would normally do, because in the Weather Service, we would just, if we get a model that keeps saying 60% or 70% or what or whatever, you're just gonna stick with that pop all the time, right? You're gonna keep saying it and saying it, but you do build up some kind of added confidence if you've always got a run after run after run saying that same pop. It does go up, but maybe not as much as I had originally thought when I did the YouTube video. Why is that? Well, I'm making a really big assumption here, which is that the background population has an equal chance for both outcomes, which may sound a little weird, and I hope to explain this here in a little bit. So one thing I kind of thought about when I did this is, we sort of see how like there's this forecast drift idea. And so it made me wonder about deep prog DT. So many of you are familiar with the term. The idea is that it's the idea of lag forecasts where you've got subsequent model runs that are all verifying it for a particular same time. And if you're seeing like a trend from run to run to run, you can more or less extrapolate that trend. You can think that trend is going to continue and be able to provide useful information for the forecast. So in this particular case, I gave an example of location drift. One thing about location drift is, of course, it's not I did that in something called Inkscape, Chad, so I can talk to you about that on the side. But anyway, so the idea with location drift is it isn't limited like probabilities are, right? In theory, you could have, say, a low track continue to move to the northwest, northwest, northwest. It's not going to bump up against an absolute limit of 100% or 0% or anything like that. But what it is limited by is projection time, right? I mean, as you get closer and closer to the event, you're basically clamping in on a solution that, I mean, the shorter the projection time is, the more, the more locked in you are to that solution. The other thing to note is that in ensembles, I mean, certainly the location drift of a deterministic single low track is a lot different than what like the probability space of ensembles is. So you have to kind of factor that in as well. Okay, so one thing I had talked about before, a couple slides ago, is that often we'll run under the assumption that the probability of having a false positive is not going to change very much. But the more I think about it, the more I realize that actually the false positive chances can change drastically based on the forecast. So what do I mean by that? Well, one of the things we noticed here over the past couple months is we've had some pretty impressive low pressure forecasts, like stuff that really have been unprecedented, not only in model climatology like what we see here, but also in real climatology. Seeing lows on the order of 970 or less being forecast. So what I have here in this figure, I mean, notice that on the right there, we're seeing a NAIFS mean sea level pressure of 976 or less, which of course strongly implies that you've got individual members that are significantly less than that as well. So I mean, this is an extremely rare event, and when I say rare, I mean related to real climatology, not just model climatology. And so I'm going to try to make an assertion here that we do focus on model climatology, and it definitely matters, but there's a very critical component with the real climatology that we may be ignoring. Why does this matter? Well, remember how I was talking about populations and, hey, in this particular case, we've got a large preponderance of green cabs versus blue cabs. Well, you could sort of make the same argument right here. Let's imagine that you've got all the scenarios, right, that are going on. In fact, we can look just here at the model climatology, and we're seeing an event that is essentially unprecedented, right? It's the minimum value of pressure for all forecast hours. So not only is it extreme in the model probability space, but a very quick cursory look would tell you that even in the real world probability space, the idea of having a 976 or less low is really unprecedented for the most part. Well, what does that mean? So the probability of that event, of the probability of a false positive, remember, it's the probability that the forecast is wrong. So let's say this is an 80% chance, right? So the probability of it being wrong would be 20%. But here's the kicker. Then you've got to multiply it by the climatology, by the realistic expectation that you would ever see that in the first place. So that would be like maybe a 1 in 100, 1 in 1,000 event, right? So I mean, the chances of having a false positive goes way up, and that's something that we have to be thinking about. If there's something that's being forecast that's, again, real climatologically rare, basically the population of events, of possibilities like that is very small. And so your climatology of the event, just by being rare, increases the chances for a false positive, and that can really drag the probability down. So it's kind of weird to think of it this way. How you even put this in operations, I don't have an answer for this, because quite honestly, I've been thinking about this a lot more recently, just not even long before this presentation, and there seem to be some pretty tricky implications here. One thing I will say is that it's one thing to know what your average climatology is, right? It's one thing to know like your probability distribution function of a model forecast, of an ensemble forecast, but really you kind of need a PDF of what the climatology itself is. Instead of just saying your average low is this, or your climatological wind speed is this, you actually need a PDF of your real climatology as opposed to your model climatology, because then you'll have an idea of what your background population is to kind of temper your expectations with Bayesian thinking, because of that accounting for that probability of false positives. All right, so I think I am at the end of my presentation, so I want to give you some takeaways here. The most important one I would say is thinking in bets, and just really start, if you haven't already, just start really making everything a proposition. When you bet on something, just put a number on it, and it can be a guess, remember, and just it'll get you thinking more in terms of the forecast decision making process instead of specific outcomes, and I think it'll really help us a lot moving forward. And then the last two takeaways I have are related to these false positives. So first of all, you got to realize they're always going to exist in some degree, and then be very careful, especially when you're dealing with rare events. Just be factoring that in. That might be kind of the sanity check there. I believe that's everything I have. So really thank you all for listening, and appreciate it. And if there's any time to take any questions or have discussion, that would be great. Thanks.
Great job, TJ. If you have any questions, please raise your hand or put it into the chat. Go ahead, Andy.
Yeah, great presentation, TJ. And I especially as you got towards the end there, and because I was already thinking about it earlier on, is thinking about all those things about what the, what's the model climate, M climate, and obviously the R climate with respect to, how the NAIFS and all that has the 1979 to 2009 CFSR, but also knowing your own, how, what are the scenarios that create some of your bigger, let's say, snowfalling QPF events, and understanding your heat waves, all your extremes, so that you can kind of compare and contrast what's being set up. And I do know that we've had a lot of, as you noted, like a lot of deepening extratropical cyclones across at least central region and beyond that have been going way too crazy. It's where I've been really liking looking at like the fifth percentile of MSLP or something as a quick glance of what's the what the fifth and 95th to kind of see what's the spread of MSLP and how much are things deepening, to really put a is that really in that realm of possibility? Because like you say, these false it seems to me more and more often they end up being false positives and the actual result ends up being weaker. But I mean, you have your cases out there. December 15th 2021 is a great example.
Yeah, for sure. Yes, and we certainly, that's why I use that as an example, was the low pressures we were getting. And I think a lot of it comes down to pattern recognition. So not surprisingly, since here in the Great Lakes we were up close and friendly with those surface lows, we were kind of the Great Lakes Sioux were talking among themselves, and it was pointed out that even models like the European tend to have more tuning towards like a tropical intensity evolution solution. So there are some real implications and issues with the models, what the models themselves are doing. So and of course that's going to be a little bit buried in a model climatology, but but that also can be diverting more and more from our climate, as you said, real climatology. So kind of the solution I think that was posited is you just gotta realize, okay, if you're dealing with like a Colorado panhandle hook low, what's really the probability of it deepening by this amount by this time? I think there has to be that sanity check. And so having a look at analogs, not just model analogs, but actual real analogs, what's actually evolved over time. How realistic are these solutions? That has to be weighed quite a bit to maybe help identify those false positive setups.
TJ, Kevin Smith has a question in the chat, if you can see it.
Okay, let me take a look here. Yeah, totally a different cab eyewitness. Maybe. You know, I think I do sort of wonder if the models are completely independent from each other. I guess that's theoretically possible. I'm not sure. It's a great question. But you do have to worry about, you bring up a point that is important, is you want to avoid covariance. In other words, you want to make sure that your inputs are not being affected by what other inputs are. So one of the things I had asked my counterpart at Detroit about, who's a modeling expert, I said, well, is there any chance that successive model runs, if you got a sequence of them, that they could have any like residue, so to speak, from the previous run, where they could in some way be influenced by that. So it's like carrying through a probability, when, in which case you can't treat them as independent inputs anymore. And he seemed to indicate, no, that's probably not the case. You probably don't have to worry about that. But with individual models like what you describe, I honestly don't know. I don't know the answer to that.